So in this one, I wanted to talk about Kubernetes operators from a more general standpoint and then get more specific. The assumption here is that there is an understanding of general Kubernetes concepts around pods, deployments, and replica sets, and essentially the different entities that exist in Kubernetes. And this sort of just takes the existing functionality to one step ahead. And to understand Kubernetes operators, one of the first things that I had to understand properly is a little bit about how Kubernetes works under the hood itself. What does that mean? The fundamental principle that Kubernetes actually runs on is the cycle between expected and desired state. So in Kubernetes, you, for example, define a deployment and you say that you want 3 replicas for this, and you spin up three different pods get spin up by Kubernetes. Essentially, if one of the pods goes down and we see the Kubernetes sees that, right, there are 3 expected replicas of this existing entity, we go from expected state to desired state, if that makes sense. So if there were 3 expected but there are only 2, we go to the desired state by making 2 pods turn into 3. So now we have 3 replicas of the same entity. And what that does is that you're now essentially working in cycles of expected and desired states. So for example, if you have a database deployment, for example, which you say that there need to be essentially 3 different replicas for the same database. So essentially 3 different pods for the database, and one of those go down, and Kubernetes sees that, right, the expected state is 3, there are only currently 2, let's spin up another one. And it keeps going in this loop of expected versus desired state, and that's how fundamentally Kubernetes works for some of the major entities that we end up seeing with replica sets, deployments, and pods and things like that. So for example, when you spin up a deployment, the expected state is for us to have a deployment, and then we have something within Kubernetes that says, right, there's a deployment that's spun up. Okay, cool, I need to spin up replica sets, and then a replica set is spun up, and then Kubernetes sees that, right, the expected state is 3 replicas, so the replica set, after it's spun up, then we eventually spin up pods. And essentially, as I said earlier, we're going in a loop of expected and desired state. And to understand a little bit more of how all of these different resources work within Kubernetes with the context of expected versus desired state. So in Kubernetes, we essentially have 2 nodes that we get out of the box. One of them is called a control plane node, and the others are just worker nodes. The control plane node is essentially that manages the bulk of this principle of expected and desired state. And then worker nodes is essentially where a bunch of resources that we create actually end up running. So the pods, the deployments, the replica sets, all of these end up running on worker nodes. And the control plane nodes is essentially the brain of making sure the entire cluster is in the desired state it needs to be running in. Now, the control plane essentially has 4 different components for the main part. There's others too, but the 4 main ones are the API server, the controller manager, etcd, and kube scheduler. The API server, as the name suggests, is essentially what ends up taking all incoming requests to Kubernetes. So for example, if I went here and I just typed out kubectl get pods, kubectl being the CLI tool to interact with Kubernetes. So if I wanted to get all pods, the API server is the one that's actually receiving this request, and it's responding to this request by looking in etcd. And what is etcd? etcd is essentially the storage solution of Kubernetes. So all the resources you create, they need to be stored somewhere. Just like any application, you have a database. etcd is sort of the database of Kubernetes, which lives on the control plane control plane node essentially. And anytime you send a kubectl command, or anytime any request that goes to Kubernetes as a cluster to do something, even if it is to apply an existing deployments file or to apply an existing pods config that lives in a YAML or whatever it is, all of that first reach the control plane node, under which it reaches the API server. Now, then we also have something called the controller manager. But before I come to the controller manager, I wanted to quickly go over a bunch of these different components and see them actually exist within our Kubernetes cluster. So we have our cluster here, and this is coming from Docker Desktop. Docker Desktop essentially just gives you a single node cluster. So the control plane node and the worker node is essentially just one, except that they logically exist in different namespaces in Kubernetes. So here we're seeing the pods across all namespaces. And if you see here, we can see the API server, we can see the controller manager, and also we can see etcd, which is the storage layer essentially. And this tool that I'm using here is called K9s, which essentially allows you to visualize a cluster in the terminal and see a bunch of different resources that are running. And yeah, so if we quickly go here and if we do kubectl get nodes, we just see a single node which runs as the worker node and as the control plane node. And if we go and describe this node, we see here that we have a bunch of these in the kube system namespace. We have the API server running, the controller manager running, etcd running, which are a different bunch of the control plane components. Now, coming back to the controller manager quickly, the controller manager is essentially the brain of Kubernetes. And the controller manager is, in very simple terms, what the operator is going to end up being, just the operator is written by us. So as I said, the controller manager, as we talked about, is meant to be the brain. So it's meant to look at expected state and it's meant to get to the desired state. And then once again, if something breaks in the desired state, we change the expected state to go back to the desired state. So theoretically, what's essentially happening is, let's say if I create a deployment which creates a replica set and then I have a bunch of pods. Now, because it needs to go from expected to desired, there needs to be something that is always watching these resources. So for example, if I create a deployment which creates replica sets, which creates pods, if something breaks, if a single pod breaks, we need to make sure that there is something that is continuously watching the deployment, the replica set, the pods, and is watching all of them together. And if something breaks, it goes from the expected state back to the desired state, which means it spins up another pod again because the number of pods changed from 3 to 2. And this is managed by specifically the controller manager. And inside the controller manager, you have a bunch of controllers itself. So for example, let's say the example we talked about, which is we create a deployment, which creates a replica set, which creates a bunch of pods. The deployment itself, let's say the deployment gets deleted, then ideally the replica set and the associated pods should also get deleted. So the deployment controller, whenever a deployment is created, is watching that deployment. And whenever a change happens on that deployment, so let's say a configuration change, or let's say somebody deleted that, the deployment controller gets triggered. And then it figures out what to do. The parts that need to get affected by a certain change here end up getting affected because these controllers are continuously watching on those resources. And this is why the controller manager is meant to be the brain of Kubernetes, essentially making sure that we go from expected state to desired state to expected state, and keep going in this loop, if that makes sense. So that was sort of the fundamentals of how Kubernetes works under the hood. And one of the other things that I wanted to get across before I move on to the next bit is that pretty much all the resources that need to run in Kubernetes, which doesn't include storage, it doesn't include secrets, those are different parts, but anything that needs to run in Kubernetes essentially boils down to a pod. A pod is the singular smallest unit in a cluster, and deployments, replica sets, all of these are essentially just wrappers around a pod, if you may. So these are the deployments and replica sets are essentially meant to be able to manage the life cycle of pods. So for example, when you create a deployment which creates a replica set which creates pods, the whole point is to manage the life cycle of these pods. The whole point is to make sure that at a single time there are 3 pods running. Because for example, if you had a YAML configuration of a singular pod, and if you needed 3 replicas of it, you would have to click apply 3 times. And you also wouldn't define any lifecycle policies around it. For example, you want a certain type of behavior to happen when one of those pods go down, for example. So all of this lifecycle management is just happening via higher level components, but it all comes down to a single small extraction unit called a pod in Kubernetes. And the deployment controller, replica set controller, everything eventually, functionally, for anything that needs to happen functionally within a cluster boil down to a pod. So here, what I wanted to talk over is how a pod is essentially created, even when higher level entities are created. So whenever a create pod simple request, let's say this has nothing to do with deployments and replica sets, but let's say we have a simple create pod request. You have a simple YAML configuration and you type in apply. What happens next is, as we talked about earlier, the first request essentially reaches the API server. The API server then talks to etcd, which is the storage layer in Kubernetes. It talks to etcd and says, please store this pod's configuration along with the metadata associated with it. And then the part that we didn't talk about, the kube scheduler. The scheduler is meant to actually watch for new pod creations in this layer, so in the API server etcd layer. And whenever a new pod is created, what it does is that it assigns a node in Kubernetes to that pod. So, for example, in Docker Desktop, what we've seen is that there is only a single node that exists. However, in theory, in an actual application, which is meant to be anything production grade, you would possibly have multiple nodes, and all of those nodes have a bunch of traffic being received, for example. So it assigns one of these nodes for the specific pod that's being created, and kubelet, which is actually a resource that exists on the worker node, is the one that actually watches for pods being assigned to nodes. And as soon as a pod is assigned to a node, kubelet actually takes that pod, takes the responsibility of creating that pod, and then it communicates with the container runtime to make sure that the container starts up. It looks at its statuses and things like that, and eventually, if there is a change in its status, if there's a change in, let's say, configuration, all of this goes back to the API server, goes to etcd, and then we go back in the same loop again. So in theory, even if we end up creating a deployment, for example, the only thing that gets replaced is that the deployment controller would see, okay, cool, somebody's trying to create a deployment, let me create a deployment resource. So actually I have that example here. So it would actually create a deployment in etcd. The deployment controller would ask replica sets to be created. So the replica set controller then creates a replica set, and then replica set asks for pods to be created. And as soon as pods are asked to be created, we go back to the same step again, where we create a pod, we essentially go over this entire process. Long story short, again, where a pod is asked to be created, it hits the API server on the control plane node, it talks to etcd, the kube scheduler, which also exists on the control plane node, watches for pods, assigns a node, and then kubelet, which exists on worker nodes, in Docker Desktop's case, our node, essentially takes those pods, creates it with the container runtime, and updates the API server in case anything changes. So that is the long story short of how Kubernetes works under the hood. And the reason why custom operators, for example, exist is because, if you can see here, one of the things that you can't do here is manage the life cycle of these deployments or replica sets yourself. So where Kubernetes operators come into the picture is, let's say if you have a database that you're spinning up, for example, and you're spinning up the database's deployment, which eventually would boil down to, let's say, 3 replicas of the pod created, right? Now, in theory, this works. And if a database pod goes down, we eventually spin that one back up. Let's say that works. However, let's say if you have something that you want, if you have some custom logic that you want to wrap around this database, let's say there are a couple of things you need to do. One, if one of those pods, let's say, would be the primary instance and the other ones would be replicas, if the primary goes down, you need to have custom logic to determine which of those pods or those pods to actually go promoted from being a replica to a primary. This isn't possible without an operator because Kubernetes is meant to be declarative in nature. So it's meant to be you defining what you actually expect, and eventually Kubernetes just spinning up those resources. You can't actually define the fact that you need to spin up a primary, you need to promote a replica to a primary when something goes down, for example. Or let's say your database starts crashing down. Kubernetes has no idea that it should maybe actually take the write ahead log and actually archive it somewhere else. Let's say send it to S3 so that when you actually spin back the databases up, you can actually use that write ahead log to actually back up your existing database interactions that have happened from a user's perspective so that you don't actually lose out on data. And all of this custom logic needs to actually be wrapped around in an operator, which is really hard to do within Kubernetes itself because one, Kubernetes is meant to be declarative, and therefore it really works on just this is the expected state, this is desired state. You can't really wrap around complex logic around promoting one specific version. Let's say you need to actually promote the version of your database, and if something starts going down, you need to actually go back, roll back to the previous version, and you need to make sure there's no form of corruption happens. And if corruption happens, or essentially some form of your database going down happens, you need to make sure you archive the write ahead log so that you don't lose out on a bunch of interactions that are happening with the database and so on. So this is why you create custom controllers, just like you have deployment controllers, replica set controllers. Here you would create a database controller which would manage a bunch of these resources. And that is what I would talk about in the next one, where I really go into the depth of operators and I actually talk about how operators really work. And I even have a code base here, which essentially goes into it. And it goes into sort of how an operator really works. And this goes into an example here where we have a custom resource. In that case, it's a database. In this case, it's something else. And it's managing those custom resources and it's wrapping around custom logic. And here we have our own controllers, just like there exists a deployment controller, a replica set controller, and things like that. So that is it for this one. And in the next one, I'll actually go into the depths of how this code works and how you actually write your own controller. And that should be it for me. And I'll be back talking about this in the next one.